Okay, so we're doing number 4 from the regression worksheet, walking speed versus population. Oh, why did that just happen? All right, so I'm going to put the data into my spreadsheet of Geogebra. So I'll put in walking population in column A. It's 14, 71, 138, 342. And then in column B, we put the corresponding walking speeds. Oops. All right, so now I've got those in there. I can highlight this whole thing, right click, and create a list of points. And there's all my points plotted over A, B, C, D, and E. And I'm going to hide the spreadsheet now. And I can only see A and B because of the scales, so I just got to change that a little bit. So my X values have to go all the way as high as 342. So I really got to change the scale of X here. Go to about 400. And then Y's have to go from 0 to 2.2. So maybe I'll make this a little bigger. There. All right, so there are my points A, B, C, D, and E, my scatter plot. Now we have to choose a function that could fit those data. So what do you think? If you were to sort of logarithm, yeah, if you were to connect those with a smooth curve as possible, it would look kind of like a logarithmic, or maybe even a square root function. Square root kind of looks like that. You could use either one. So on your test, you know, if I asked you what kind of function would you use to model this, you would say either a logarithm or a square root function has the same shape as this data. So in the input, I want to do a regression, which I believe if you type can't remember how to do it. That's okay. That's what we have. This sheet in Moodle, Geogebra reference sheet. Tells you how to do everything that you need to know in Geogebra. Okay, so to find a regression curve, use one of the following commands. Logarithmic regression is fit log and then the name of the list of points. So fit log, square bracket, and then my list is titled list 1. That's the list of all my points. And if it's a logarithmic equation and the equation is over here, I just have to expand this so I can see it. Negative 0.04 plus 0.39 ln of x. All right, so there's my regression equation. And then the question asked me, oops. To write down your equation and the value of r squared. Oh, how do I get r squared in GeoGebra? Let's see. After doing a regression, to find the value of r squared, use the command r square list of points function. And the function is the name of the regression equation. Okay. So r square. r squared, and then see how it pops up asking you for what it needs. It needs the list of points and the regression equation. So you hit square bracket. My list is list 1. My function is called f of x. And my r squared value is 1. I'm just seeing if I can maybe change the rounding, because that doesn't matter. Okay, so r squared is about 1. All right, so we've got the equation, we've got the value of r squared. We want to use the equation to predict the average walking speed of a person in a city of 100,000 people. So 100,000 people, population size, is that x or y in my equation? X, yeah. So I want to put in 100 for x, because this is being measured in thousands. So I just have to evaluate f of 100. So if I wanted GeoGebra to do that, I could graph a vertical line at x equals 100, right? And then what I want to know is the y value over here, right? Because I would like to know the coordinates of this point. When x is 100, what is the y coordinate on my graph? So I can find the intersection of these two. Intersect curve 1, curve 2. Let's try that. Object 1, object 2. Function is f of x. And that line has a name b, so I got to intersect it with b. And it gives me the intersection point is f 100, 1.74. So 100 is the size of the population, 100,000. 1.74 is the walking speed. 1.74. You could also just type that into a calculator, right? It should give you 1.74. And let's see, the units on that were feet per second. So in general, looking at this curve, what can you say about walking speed as a function of the size of a city? Yeah, as population increases, walking speed increases. But it increases more and more slowly, right? The difference between a small city, like at point A here, that has 5,500 people, versus, you know, a pretty large city like C with 71,000 people, there's a big jump in walking speed. But then from C to F, right, there isn't quite as big a jump, or even C to D, there isn't quite as big a jump. All right, so we've got US population in millions. We're supposed to fit a linear function and an exponential function to the data, and then write down the equations and the r squared values, and say, is either one a good fit? Use both of the equations to predict when the US population will reach 335 million. Okay, so let's follow the same procedure as we did before. So I need the spreadsheet. And I'm going to put the data in there. 1, 11, oops, here, 11, 21, 31, 41. And then the corresponding populations are 203.3. Oops. $281.4 and 308.7. All right, so we highlight all those, create a list of points. And then I can just hide my spreadsheet. All right, so I can't see any of them because of the scale. So my x's have to go from 1 to 41. So I've got way too many x values showing. And then my y's are all in the like 200 to 300 range. So I need to see a lot more y values. There we go. There they are. Okay, so I'm supposed to fit a linear function and an exponential function. So I think the command for fitting a line is fitLine. And then we just have to choose the list of points, which is list 1. And there's the equation of my line. And then I need to do fit exp, fits an exponential for list 1. And there's my exponential, the curve. It's hard to tell the difference between those two. Let's make one of them a different color. We'll make them both a fun color. All right, so the line is in blue and the curve is in pink. So is one of the, oh, sorry, yes, you're right. The line is pink and the curve is blue. Okay. Is one of them a better fit than the other? If we get the R value, that could tell us. Just by looking, does it look like one is a by far better fit than the other? You think the blue is better? The blue does seem to hit every point. The pink seems to be off a little bit at C and at A, but they're very close, right? Either one could be used as a good model. The blue does look a little better. Okay, so if I want the R squared value, I need R square. The list of points is list 1. And then my function, well, let's do the lines R squared first. That's object A. So R squared for the line is 0.99. And then R square for the exponential, which is f of x, is 1. So the exponential is a little bit better. So I just wanted to write down, this is for the line. This is for the exponential. Okay, so we've got all the two equations, the exponential and the linear equation, the R square value for each. So we know that the exponential is a little bit better than the line. And then the last thing they asked us to do was use both of these models to predict when the US population will reach 335 million. So 335 million people, is that an X or a Y value? Y. Yep. because it's right here. It says that Y is US population, right? X is time. So I'm going to put in 335 for Y into both of those equations, and I want to solve for X. So I want to set 335 equal to my line, 2.66x plus 197.92, and solve. And then I also want to set 335 equal to my exponential, 201.17 e to the 0.01 x, and solve for x in both of them. And each one will give me a different value of x, which represents a different year when the population will reach that value. For y, I put it in for y. Yep. For both of them, you put 335 in for y, because 335 million people is a y value. So we can have GeoGebra solve this for us, but you know, it might be good practice to do these algebraically. So for this first one, if I solve for x, I just have to subtract 197.92 from both sides. Pull up a calculator. Okay, 335 minus 197.12. So 137.08 is equal to 2.66x. And then just divide both sides by 2.66. And you get x is 51.53. So x was measured in years after 1969, right? So I just add 1969 to that, and you get the year 2020. So this is during 2020, about halfway through the year 2020. All right, and then this one to solve, first thing you want to do is isolate the exponential. So I'm going to divide both sides by 201.17. So I have 1.665 is equal to e to the 0.01x. All right, so the variable is in the exponent. How do you deal with that? Logarithm, yeah, take the ln of both sides. I always use ln, but another sort of double reason to use ln is that the base is e here. So you can always use it, but I definitely use it when your base is e. Right, so all I'm doing is just taking the ln of both sides, right? Because that's the cardinal rule of equation solving, is if you do it to one side, you have to do it to both sides. So what I'm doing is I'm taking the log of both sides of the equation, taking the ln of both sides of the equation. Now the ln of 1.665, that's just a number. Let's figure out what that number is. It's like 0.50998. And what is the ln of e to the 0.01x? 0.01x, yeah. The ln of e to some stuff is the stuff, because ln and e to the stuff, those are inverse functions. So that's why we took the ln of both sides, is because the ln undoes exponential. Right, so this is just 0.01x. Those two undo each other. You can also think of it if using properties of logarithms. We have this property that when you take the ln of something to a power, you can take the exponent and put it down in front. So this is 0.01x times the ln of e. What's the ln of e? Close. 1. Yeah. So this is 0.01x times 1, which is 0.01x. And if you forget what the ln of e is, you've got a calculator, right? Just hit ln of e 1. All right, so A common log or the ln, yeah, doesn't matter. Yeah. All right, so the last thing is just divide both sides here by 0.01. So I've got that 0.50998 number divided by 0.01, and I get 50.998. That's almost 51 years after 1969. And we get 2019. End of 2019. Okay, so we want to write a formula for a function whose domain is all values from 6 to infinity. All right, so if a function doesn't have all real values as its domain, that means either there's a fraction, right, and you have to eliminate things that make the denominator 0, or it's a square root and you have to eliminate things that make it negative. So which one of those do you want to use? Square root, yeah. Because a fraction will only eliminate one value, right? Or maybe two values if there's two factors, right? But we want to eliminate a whole bunch of values from the real numbers. So a square root would work. So if I do f of x equals the square root, now what should go under there so that I can only plug in things that are 6 or bigger? X minus 6. Right? That way, no matter what I plug in, from 6 to infinity, I'll always get a positive value. Does that make sense? So the only x values that can plug into this function f are numbers bigger than 6. Otherwise, when I subtract 6, I'd get a negative. All right, a function with symmetry about the origin. So you might draw yourself a picture to start. So it means the double fold thing, where like if you fold it over the x-axis and then the y-axis, so you're folding the axes into like quarters, the two pieces would lay on top of each other after the two folds. So classic example is this guy. What's the formula for that? X cubed. All right, an equation of a horizontal line. So y equals, yeah, because every point on this line has something in common, right? Every point on this line has some x coordinate and then the same y coordinate. Because no matter what point I want to plot on here, I would go over some amount, left or right, and then you go up the same amount no matter where you are. So they all have the same y coordinate. And let's just say in this case it could be 6. Right? Or y equals 11, you know, whatever. That's the equation of a horizontal line. Okay, two lines whose graphs are perpendicular. Yeah. They have to have opposite signs for the what has to have a mx plus b. Yeah. Yeah. So m has the slope. They have to have opposite signs. What else? It's not just opposite signs though. It's not just one's positive and one's negative. No, reciprocals. If they're parallel, they have the same slope. Parallel, same slope. Perpendicular is opposite reciprocal slopes. So I could write y equals 2/3 x plus 7, right? You can pick any y-intercept, that's just random. And then my other line, we'll call this one y1. This one will be y2. What would its slope have to be? minus 3 over 2. And what's its y-intercept have to be? Doesn't matter. You pick anything you want. The y-intercepts don't matter at all. The only thing that makes two lines perpendicular is their slopes. So the 7 and the 18 were both completely random. The only thing that's important here is the 2/3 and the negative 3/2. Yes, a horizontal and a vertical line would also be correct, yeah. And they don't have to both be 3, right? It could be x equals anything and y equals anything. A horizontal and a vertical, no matter where they are, will be perpendicular. Good. All right, a piecewise defined function that is increasing from 0 to 4 and decreasing on negative 3 to 0. So I'm going to draw a picture of it first. I think that will really help me. So here's my axes. Put in the important points here. Right, because these are x intervals, 0 to 4 and negative 3 to 0. So I marked them on the axes. And it has to be increasing from 0 to 4. So if I draw the simplest thing I can that's increasing would be a line. And I'm going to encourage you when you're doing this kind of problem, keep things as simple as possible because they're not meant to be tricky, right? They're not meant to be hard. All right, so it's increasing from 0 to 4. So it's increasing because when I start at 0 and move to the right, that line is going uphill. And it has to be decreasing from negative 3 to 0. So if I start at negative 3, it has to decrease until 0. So there's a picture. What function does that look like? Absolute value. So we could just pick absolute value. Yeah. Wouldn't be this exact picture. I would have to make it go down to the axis, but that's a piecewise function, absolute value of x. It actually is, we talked about the definition. The equation of the line is just y equals x if x is bigger than or equal to 0, and it's the opposite of x if x is less than 0. So the function has the same value at 0, whether x is positive or negative. So I just put the or equal to on one of them. So because you get the same y value in either formula. So it's sort of like a nitpicky grammatical thing when you compare it to, like, say, English. It's like putting it in both places is kind of being redundant. Like the name of the boy named George is George. Like, it's not untrue, it's just weird. Yeah. So you can put it in both places, but we don't. All right, so a function whose rate of change is constant. A linear function. That's the definition of a linear function. A function whose rate of change is constant. That's the slope. The slope is a constant rate of change. So any linear function, y equals mx plus b, just make up a line. A function that does not have an inverse. Y equals x squared. Any function that fails the horizontal line test. You could use absolute value of x. You could use x squared. Any function that fails the horizontal line test. All right, a quadratic function that has no real zeros. So we know that every quadratic function has two zeros, but sometimes they're real and sometimes they're imaginary, right? So we want one that has no real zeros. Yeah, a function that can't be factored, a quadratic function that can't be factored. Graphically, what would a function look like if it has no real zeros? It wouldn't touch the x-axis. So we have to, if we want to start by drawing a picture, so it's always a good way to start if you can't really come up with it off the top of your head. You want to draw a quadratic, and all quadratics look like parabolas, right? So we want a parabola that never touches the x-axis. Can you come up with a potential formula for that? Yep. Just take a vertical shift of x squared. Yeah. Just shift it up and it won't have any x-intercepts. And Eileen was saying something that can't be factored. This can't be factored, right? X squared plus 4. Yeah, that's as much as you can factor it, unless you want to use imaginary numbers, right? We could factor this to x plus 2i, x minus 2i. All right, a transformation of any parent function. Okay, so you can choose any parent function you want. X squared, square root x, absolute value, x cubed. We've got a whole bunch of parent functions, 1 over x, whatever you want. We want to create a horizontal stretch by a factor of 2, a vertical compression by a factor of a third, and a horizontal shift 4 units to the left. All right, so first let's pick a parent. Have this be f of x equals, what do you want to use? So x squared would be fine. One reason that I'm not going to use x squared is because it's hard to distinguish between inside and outside. So I'm going to pick something where it's really obvious what's inside and what's outside. And afterwards, I'll do it with x squared because that one's just a little subtler. Okay, so let's choose square root x for our parent. Okay, so then my transformation we'll call g. Right, so we want a horizontal stretch by a factor of 2. So horizontal things, horizontal changes, are they inside or outside changes? Inside. So inside the square root, I have to do something. What do you do to create a horizontal stretch by a factor of 2 inside the square root? That's a shift. That will create a horizontal shift if you do x minus or x plus. A stretch or a compression is multiplication. Yeah. So this is going to be inside the square root. I have to multiply x by something. 1/2. Inside slash horizontal changes always are sort of the reverse of what you think they should be. Yeah, so it seems like you should multiply by 2 to create a stretch by a factor of 2, but in fact you multiply by 1/2. And then we want a vertical compression by a factor of a third. Vertical changes are outside, so outside the square root. Stretches and compressions are multiplications. I'm going to multiply outside the square root by something. What am I going to multiply by? 1/3, yeah. Because vertical changes are always exactly what you expect. They're always very straightforward. So if you want to shrink by a factor of a third, you multiply by 1/3. And then finally, I want a horizontal shift 4 units to the left. Okay, so because this is horizontal, it should be under the square root, right? And if I want to go 4 units to the left, plus 4, because it's horizontal, it's the opposite of what you expect. Let's do x squared, because x squared is a little let's have h of x be x squared, and then j of x will be the transformation. So we already know exactly how to do this. We have to multiply the outside by a third, and the inside is 1/2 x plus 4. So I'm using the letter h instead of the actual function here. And then I can say 1/3 times 1/2 x plus 4 squared. So the inside change is all the stuff that's inside has to get squared, and the outside stuff doesn't. When you square it, yeah. All right, so let's say 2. I'm not going to promise the answer is going to come out pretty because I'm making this up off the top of my head. Okay, so the first thing you want to do when you're solving an absolute value equation is isolate the absolute value, right? So I just want to solve for that. Okay, so I'm going to add 6 to both sides. So I have 2 absolute value 3x plus 4 equals 18. Then divide both sides by 2. So I have the absolute value of 3x plus 4 equals 9. So if the absolute value of something is 9, that means that something that I took the absolute value of could have been 9, but it also could be -9, right? Because the absolute value of -9 is also 9. So that means that 3x plus 4, this stuff that I'm taking the absolute value of, that stuff inside there could be 9 or it could be -9. So I set up 2 different equations. 3x plus 4, it could be 9, or 3x plus 4 could also be -9 because the absolute value of -9 is also 9. And then you solve both of these equations. So let's see, if I subtract 4 from both sides, I get 3x equals 5. So x is 5/3. And over here, subtract 4, -9 minus 4 is -13. So x is -13/3. So you've got 2 values of x that actually satisfy that equation. Yep. So to get rid of the absolute value bars, you have to translate this into 2 separate equations. Okay, so this is class 41, number 5. Okay. Figure below shows the number of people in a certain country that are age 65 and over with projected figures for the year 2010 and beyond. Complete parts A and B below. All right, let's see what they asked. Okay, so first, X is supposed to represent the number of years after 1899, and Y will represent the population age 65 years and over in millions. Use your graphing utility to find the model that best fits the data in the bar graph. Okay, so my data is 1900 is going to be year 1, right? Because we're years after 1899. So your data is going to be like 1, and then 1910 is 11, 1920 is 21, 31, 41, 51, etc. And then, so these are your X's, and then your Y's are going to be 2.8, 3.5, 4.5, etc. Right? So I want to put all this data into Geogebra. Okay, so putting this in here up to 151. All right, and then 2.8. All right. Okay. All right. So I've got all my data plotted. It does not look very good. My x's need to go from 1 to 151, so I need to see more x values. That should do it. And then y's go from 2 to 89, so I'm looking at more than I need here. All right, there we go. So what kind of function might you choose to model this data? Square root? Square. So fit, I'm going to do a poly. Fit poly is fit polynomial. Yep. And it tells you that you have to give the list of points and then what degree you want to use. So my list is called list 1, and I want to use degree 2. So there's a quadratic model. I can get an R² value by typing the list of points and then the function f of x. And I get R² of 0.99. Not bad. But it does ask for a model that best fits the data. So is it possible that I could find a better fit than this quadratic? Yeah, we could try an exponential. Fit exp, list 1. It looks better. Let's make these different colors here. Okay, so pink is the quadratic, purple is the exponential. It's kind of nice that they also changed the formulas to the appropriate color. All right, so let's get an R² for the exponential. So I need to type the list of points, and then the exponential function is g of x. 0.97. All right, so the quadratic was actually better. Do you think we can get better than 0.99? Do you think there's a better function we could use? Logarithmic increases but bends down. Oh, I think you're thinking of maybe logistic. Logistic is good for population growth. Let's try that. Let's fit logistic. That's the one that's got the S shape. It starts out increasing but then bends down. Logistic list 1. All right, so there's my logistic function h. It's in black here. Change the color. Get green. All right, so that looks pretty good actually. Let's get an R² for that. .99. So we can't tell which one's better. Rounding. Let's do 5 decimal places. There we go. All right, so it looks like the logistic is better. So this 0.98779, that's our quadratic. Then we tried exponential, it was not quite as good. And then we tried logistic, which is a little bit better than exponential. So let's put the logistic function into my math lab, see what it does. Oh, nice. Okay. Oh, so they meant find the model from my list that best fits. Okay. So none of them match the data well. This fits the data in the bar graph. Okay, so I guess we should just graph all of these. So we've got some exponentials. There's a power function. We've got a line, some lines, and some log functions. It's probably not the log functions. All right. Let's delete, delete, delete. And I'm just gonna type these in here. I don't know if I need a times, but I'm gonna put it in. Sorry, I have to just sit there and watch me do this. Okay, get them all typed in. So then we got to decide which one looks best on this data. That one I think we can eliminate, right? This one that I'm looking at right here, it's bold. Let's see, change the color quickly. So it doesn't look like it goes anywhere near my data. So I'm just going to delete it because it's not that one. And then this one also looks like it doesn't go anywhere near my data. That one, yeah, so let's delete that. And that one, nowhere near my data. Okay, so the rest of them are kind of contenders, right? They're all sort of in the right vicinity. This one looks pretty good, the one that's highlighted now. This line looks pretty good. This line looks pretty good. That is pretty off, and that's pretty off. So let's get rid of this one and this one. And then we can get our square values for the remaining. Actually, this line is not nearly as close as these two curves. Let's get rid of that line. All right, so we'll get our square values for these two. It's probably going to be this one because it bends up with the this one ends up going away from the data at the end. So it's got to be that one. 3.115 times 1.024 to the x. B. Rewrite the model in terms of base E. By what percentage is the 65 increasing each year? Okay, so in terms of base E, 3.115 times 1.024 to the x. Okay, so if I want to write this in terms of base E, 3.115 stays the same. So it's going to be 3.115 times E to the what? Right? And we call this thing kx. How'd you get that? Uh-huh. Yeah, so we can say, well, 1.024 to the x has to equal the same as e to the kx, right? Because the 3.115s are the same already, so we just ignore those, right? Ignore. And then 1.024 to the x has to equal e to the kx. They both have an x in there in the same spot, so you can just ignore the x. And so 1.024 has to equal e to the k. And then how do you solve for k? We're going to take the ln of both sides. So the ln of 1.024 equals the ln of e to the k. The ln of e to the k is k. And the ln of 1.024, I can do my calculator. Is 0.0237. So when I come over here, so I've got 3.115 e to the 0.0237x. Yeah, those two functions are the same. Yeah, so let's actually look at those two things graphed. So I've got this one graphed here. Let's do this one in red. Okay, and then the thing I just came up with, y equals 3.115 times e to the 0.0237x. And it graphs right over the line I just had, right? They're the exact same function, just written a different way, like synonyms, right? So if I change this to graph it in blue, just standard blue. I was hoping that when oh, it does. Look, see, now my line is purple because I did one in red and one in blue. So you can see that they're the same curve. Base E, round to 3 decimal places as needed. So this is 3.115 e to the 0.024 because they told me 3 decimal places. There we go. Okay, by what percentage did the 65 and over population increase each year? (2.4%). Yeah. You can look at 1.024, that's called your growth factor. Okay. So when you multiply something by 1.024%, this 1 represents 100%, right? You keep 100% of what you had, and then you increase by 2.4%. So this is 124%. Oops, got that wrong. Haha. This is 102.4%, which is a 2.4% increase, right? That 100% is just what you had before. 2.4% more is what you have now. So from the previous year, increased by 2.4%. Okay, so then you've got two equations with two unknowns. 24 equals AB cubed and 6 equals AB to the first. Let me just explain this again. Okay, so cardinal rule of equations is you do the same thing to both sides, right? So if I divided this side by 6, I'd have to divide the other side by 6 also, or something that's equal to 6, right? So if I don't write a 6 there, that's okay, as long as the thing I write there is the same thing as 6. And a times b to the first is 6, right? That's what this equation says. So I can divide this side by ab to the first, because 6 and ab to the first are the same. So I'm doing the same thing to both sides of this equation. So 24 over 6 is 4, and on the right here, the a's cancel, and I end up with b squared. Right? B cubed over b to the first is b squared. So b is what? 2. Why isn't it plus or minus 2? Right, but positive 2 squared is 4, but so is negative 2 squared. Negative 2 times negative 2 is also. So technically, the answer to this equation is plus or minus 2, but I'm purposefully leaving out the negative. Yeah, any part of our definition of an exponential function is that b must be positive. That was part of the definition. So any a times b to the x has to look something like this or like this, right? Never goes negative. So b can't be negative. So b has to be 2. And then you go back to your other equation, 6 equals a times b to the first. Plug in a 2 for the number you know. 2 to the first is just 2, and solve for a, and you get 3. So we have, my equation is y equals 3 times 2 to the x. It's usually easier. I picked a hard one. Let me pick an easy one. If I have 0, 4, and 2, 8. Let's try that. Okay, so I know my function is a times b to the x. Put in one of your points. So I've got 4 equals a times b to the 0. But anything to the 0 is 1. So immediately I know a is 4. All right, so then I use my other point to 8, and I replace a with a 4. So I have y equals 4 times b to the x. And then plug in my point, 8 for y, 2 for x, and I solve for b. I made a poor choice of points here. Okay, so b squared is 2, which means that b is the square root of 2. So my function is y equals a times b to the x, and a I know is 4, and b is the square root of 2. So if you're given the y-intercept, it always ends up as a. The y-intercept is always a.